We are the world's largest water jet manufacturer in the world. Ultra high pressure water jets used for cutting all sorts of different materials, different thicknesses, and so forth. And right now we have a few samples that are going around. I guess we'll just circulate it back to the front. You have a beveled piece, which is used with our dynamic XD 3D cutting head. There's a sample of some G10 material, and then as well as a stack piece. And there's actually different materials that are stuck together. And that's one of the different unique things that you can also do. You can actually stack cut different materials, as long as they're relatively within the same hardness. So those are going around, and then we'll go ahead and get started here. So we'll take a look real quick at the agenda today, and I won't read point for point because I'm pretty sure everybody will read it and it'll get too boring. But we'll look at some of the different future emerging opportunities. We'll look at comparing water jet technology to a few of the main competitors, which are lasers, EDMs, and plasma machines. And then a few applications that you didn't think were possible, and as well as how Flow looks at historical trends and how we can kind of predict the future of why water jets are going to be as prominent as we believe they are going to be. And then I think there's one more part which kind of looks like it's a circle with little edges around. It's in the back right corner there. That's a sear ring, and then I'll explain a little bit of the significance of that part as well. So again, some of the different types of technologies that we're going to look at are plasma, laser, and EDMs. This is actually, I'm not sure how well you can see it, but this is actually a split cross-section of a water jet cutting head. So you can kind of get an idea of how these work. So what you do is, see if I can get a laser here. What you do is you take ultra high pressure water. And the thing is when you pressurize water to 60,000, 87,000, 94,000 PSI, you can't cut with pressure. You need to convert that into velocity. So what we do is we actually force feed it into a jewel orifice, and this can be like a ruby, a sapphire, a diamond, and it has a little pinhole into it. And so when you force pressure through that pinhole, what converts, what comes out of it is velocity. So you have your ultra high velocity jet of water coming down. Now with that water, you can cut some of the softer materials like rubbers, plastics, gaskets, even some really thin aluminum you can actually cut with water only. Once you get into anything that's a little bit thicker, a little bit harder, into your steels, composite material, glass, you actually need to introduce abrasive into it. And abrasive is the January birthstone garnet, just mined, typical abrasive. That will actually go down a mixing tube, 3 to 4 inch long mixing tube, and then out comes your abrasive slurry mix, and then that's what you can use to actually cut a lot of these harder materials. So some of the common challenges previously, about 10 years ago in 2D cutting, and then now in the age of 3D cutting, they shared common challenges. There's 3 main common challenges. First, water jets naturally have taper in them. So if you were to imagine sticking your thumb over a garden hose, it would fan out. So that's what happens when you're actually shooting it down. It fans out and it causes a taper, so you aren't going to get your 90-degree walls. Another occurrence is stream lag. It's where the top and bottom stream don't match up. There's kind of a delay. So if you were to get that hose and kind of swing it around left and right, there's kind of that whipping effect, and that's kind of the same idea. And then the last one is just predicting the stream behavior, how it's going to act to the part based on your material, your hardness, thickness, and so forth. And that's just ideal when you're looking at cutting really accurate parts. Now here's kind of a breakdown of the taper and the stream lag. So first, your taper, you can see it right here. This is kind of the natural occurrence. If you're going fairly slow, as you speed up, that taper doesn't really have a chance, so it starts to converge on itself. The main idea is what you want is right in the middle, where you get your 90-degree walls. This just kind of shows how the fanning action happens inside the workpiece. Now here's the trailback, the whipping analogy with the hose that I was mentioning. What happens is the top of the stream here doesn't necessarily match the bottom. There's going to be that delay time, especially when you go with thick material. So what happens is when you actually are coming around a corner of a piece, even though the top part has already came around the corner, the bottom part is still coming around the stream, and it whips out. and it causes just a really inaccurate, the corners can be rounded off. You aren't going to have that sharp 90-degree wall. So one of the things that Flow invented and patented was the dynamic Waterjet back in 2001. What that did was it's an articulated cutting head, so it's able to move around, but it's all computer driven. You can't tell it to bend at 10 degrees and cut. You basically put in your material type, your thicknesses, and then from there it calculates already how much it needs to articulate itself. So what we were able to do is we were able to bring tolerances from 5 thousandths, around 5 to 10 thousandths, down to approximately 3 thousandths. And right now we're able to bring it even further down to about 1/1000th of an inch. Your speed as well has increased. What it does is it slows itself. It waits for the bottom stream to show up at the corner. And as soon as it breaks around that corner, then it speeds up. And so we're actually getting 2 to 4 times faster cutting. Here's a diagram of taper again. With dynamic Waterjet, what it's doing is, again, you're getting your taper, your little V cut shape. What it's doing is it's tilting across so that all of your taper is on your waist part of your material, and then you're having a 90-degree wall on your part side. Here's a quick video. We won't watch the whole thing because it goes for a little bit of time. But this is your traditional standard 3-axis, your front and back, left and right, up and down, Z-axis. And then this is your dynamic Waterjet, and you can kind of see it tilt a little bit. And they're cutting the exact same parts, same PSI, but this one's already done, as this one's, still trying to catch itself up. Some of the things that Flow pushes is pressure equals productivity. So as we're constantly trying to ramp up the pressure, you're going to be able to cut faster. If you think about the concept of each granule of garnet being used to cut the material, if you increase the pressure, each granule has more cutting power. So you're actually using less of your consumables when increasing your pressure. So about 10 years ago, Flow introduced 60,000 PSI. The rest of the Waterjet market was a little hesitant to jump into that field, coming from about 40, 55,000. Went to 60,000. Now that everybody's caught up, Flow's introduced 94,000 PSI, so that's what we're currently operating. In this bunker, this is actually a picture of our facility out in Seattle, Washington. In that bunker, there's a full-on cage. You go inside, and we're actually testing in the 140,000 PSI range is what we're going for. One of the difficulties with that is this is a cold cutting process, so the stream coming out is extremely cold. It's not like a laser or plasma where it's burning the material. What happens is when you pressurize water, it freezes up, it gets extremely cold. So now that we're going to the 140,000 PSI range, we're actually dealing with issues where ice particles are coming out of the water as it shoots out. So that's one of the things that we definitely are trying to work around and get past. Again, 140,000 PSI is what we're looking at. This is a picture of 2 dual intensifier pumps. If you're wondering why there's 2 pumps, typically what we do for higher production companies, if one goes down, if there's a leak, you can actually shut it off, turn the power on to the other one, and continue production. And then here's this is actually a diesel pump that is used alongside with Caterpillar that we paired with. And that's for surface preparation, stripping off the road. We actually use pressure to strip away material down to the bare metal on like ships and dry dock and so forth. So here's a few different applications that you can use a Waterjet for. We use them in the medical field, doing surgical devices. You can see the tolerances. Looking at some of the smaller, intricate steel work, as well as some copper electrical work. And our first start with Waterjets, we actually started out cutting baby diapers. So what they were using for the little hourglass shape, they were actually using metal saws, and there's metal shrapnel getting into it, and obviously that's not a good thing, putting those on your kids. So we did it with pure water. Now it's pretty much evolved into everything. We cut out Fig Newtons, little chicken nuggets that have like little shapes on them, all the way to the Dreamliner airplane, the Boeing airplane, mainly made out of composite material. Obviously, Waterjets are great for that cold cutting process. So we pretty much can cut any material out there. And even down to some of the smaller parts, some of your little SanDisk memory cards, those are all cut with Waterjets as well. Again, here's another look. This is actually a part from one of our employees doing some custom motorcycle parts for his chopper. Some titanium parts, stainless steel. And then also, not only are we able to cut virtually any type of material that certain things like EDMs, plasmas, and lasers are restricted to, we're actually able to cut through very thick material. Again, it's an erosion process. It's not melting, not cutting at it. So here's some 4 inches of titanium, some 9-inch material, as well as up to 24 inches of stainless steel. This is out in Romania, one of our customers doing. I believe it's a hatch for submarine doors. So we can definitely get through that kind of material. This kind of work, I believe they were traditionally milling it, and it took about 400 cutting hours to do that. With the Waterjet, we brought it down to about 70. So still relatively, 70 hours still a lot of time, but compared to 400 of letting a mill machine go off, it's definitely a great improvement. Now, I just want to touch real quickly on lasers and plasmas, and later on we'll look at EDMs. But one of the big differences is, again, this is a cold cutting process. With your lasers and plasmas, you're getting a heat-affected zone. So basically what that is because you're melting, you're burning it. Because you're burning it, some of the metal microstructures change within that. The makeup of the material changes. It can actually harden, and then it becomes brittle. So not only does it change it, you also have to do secondary finishing to it. So grinding it down, sanding it down, so forth. And then that can also wear out your secondary processes, the machines that you use to grind that down. So here's a real quick comparison look, and I won't read the entire thing, but looking at plasmas, they start out at the lower bottom of the price spectrum. Your lasers are beyond your Waterjets. They can go easily into the $1 million range. And then your EDM, so looking at things like materials, you're restricted to conductive materials when you look at EDMs. Some of your materials, like your lasers and plasmas, they can't do things like stone or like mirrors or glass. If you think about it, shooting a laser down, it's just going to bounce back up and damage the laser itself. EDMs are, can do thick materials, but when you look at your lasers and plasmas, you're looking anywhere from like the 1 to 3 inch range. And then when you go to your high def plasmas, you're looking at around 4 to 5 inches. But again, your Waterjets, overall, anywhere from 60,000 up to about 300, 400,000, can cut virtually any material, and then can also do thicknesses well above 24 inches. And again, here's some of the different applications that people have used them for: rubber, plastic, leathers, some of the harder materials, stainless steels, mild steels. And then kind of down the middle, some of our most, common materials that we cut. What's interesting is, even though we consider titanium very hard, it's still something that we're looking at, but we actually cut titanium much faster than we cut stainless steel. Just by the reaction of the abrasive, the water, and the metal itself, we're actually able to cut titanium much quicker. And we're going to take a look at some of the different opportunities, some of the past, what's introduced the past to the present. And again, Fig Newtons, they were actually traditionally cut with a blade. But the filling would get caught up onto that blade, so every time it would pull up, it would just take material with it. So they were looking for an easier way to be able to cut these, have less material waste. What's interesting with Fig Newtons is they actually use less filling now. So when the blades were actually pushing it, it would bend the cookie side over it so it actually looked thin. With the Waterjet, you get clean cuts, and so it actually gives the illusion that there's more filling into it. So in retrospect, they're actually able to save a bit on some of their material. Again, some of your military work, composite material, some 5-axis turbine work, stone inlay work, and again, some of your titanium, some of your thicker materials are capable. So looking at pure Waterjet, like I mentioned before, if you were to take the abrasive out of the equation, you're actually able to do things like foam, rubbers, gaskets, belts. You can often run multiple heads all at once to increase your production. And again, dealing things like with food, so your candy bars, your chocolate candy bars are cut with Waterjets. as well as your fish, chicken nuggets, like I was mentioning before. It's a situation where you have no human hands touching it. It's much healthier, much cleaner, and a kind of a neat fact is that when we cut chocolate bars, when you cut with water, it hazes the chocolate. So we actually pressurize melted cocoa butter, and we cut with cocoa butter, shooting through it. So and you don't want to stick your tongue under that because it's not good. So some of your other different things like food, your carrots, cake, Hostess cakes. You can actually see in this picture, there's actually not a lot of downward or lateral pressures that are impacted on it. If you go visit our booth, booth number 3435, we actually are cutting out some live demo plates on our 5-axis machine. And you can see that it's not really bolted down really tightly. It's again, very, very little lateral and downward movement. Some of the other different applications you may or may not have thought were possible were ceramic stones and tiles. Great for stone inlays, a lot of like intricate work. Virtually any countertops, stone countertops that you look at in homes were done with Waterjets. When you're looking at your saws, you can't really bend around corners. You're doing your just standard directions. So with these, you can do your intricate sinkholes and so forth. Glass is another great application. This is actually one that a customer of ours did in Las Vegas for a casino. Some stained glass work. This is a local artist down here in California who cuts out stained glass work and then fuses them, heats them up together and fuses them together. Some real thin walls. The Flow Waterjet was actually helped cut out some lenses that were used for the Hubble telescope. And the walls were so thin where they held a structure, but as soon as you touched them with human hands, they would actually fall apart and crack. So that's how thin we can get these walls. Laminates and composites, and this is kind of the section where we say we look at the past to kind of predict the future. So back in the 60s and 70s, aluminum was booming in the aerospace division, and that's where we kind of got our big start in the 80s, is we had a lot of machines in the aerospace industry. Now you see everything that's in aluminum, it's everywhere, laptops, cars, vehicles, all that. Now you can see airplanes like the Dreamliner that are all made of composites mainly, and you can take that and look at that as opportunities for composites to go into vehicles. You see prosthetic limbs that have composite material in them. Even things like laptops will have composites in them. So we use that as a great indicator. The reason why it's so good on composites is, again, it's not burning, melting the material. It doesn't pull out any fibers, doesn't cause any delamination, any stress on the material. And prototyping as well. So this is a chopper that was done by Orange County Choppers that they made for us. And so it's great for prototyping work. If you're looking just to do some real quick one-off parts, you can cut out the shape in virtually any material, and it's just really quick. There's no tool changes. You can basically load a piece of aluminum, have it cut, switch it over to some stone or glass, and have it all cut. You don't have to switch out the cutting head or do anything like that. Milling is also another great application. It's specialized the way we do it, but basically we set a certain speed for the Waterjet to pass. Each pass controls a certain depth. So that's how we can, so as we bring it back and forth, we're actually able to control certain depths. And our accuracies can be about 0.02 of an inch of accuracy when we're milling with this. Again, here's a couple more examples. Turning was also a great application. Being able to rotate in different directions actually gave us different surfaces. And again, we also apply meshes or abrasive to it, just like sandpaper. So your 80 mesh is a little rougher, 120, 220 is a little bit finer edge quality. Rotary Axis, which was done back in 1997 by Flow, it's lost ground since due to some of the 5-axis work that we've been introducing, but best suited for your round stock material. And this is kind of an example of an old Rotary Axis where we hooked it up and would rotate and just have the edge of the stream index on it. Hole drilling, these are great. What's interesting about Waterjets is, unlike your typical drill presses and so forth, you can make your holes. You can make your holes in these, but you also can do angled holes, as well as you can do square-shaped holes. And so We've done work with the military where we actually take P900 body armor and we create angled holes onto it. And what they do is they put that underneath the vehicles. So when they roll over IEDs, explosives, the blast will actually hit it and deflect all of the energy out of it. So we did some testing for the military. They actually sent back a picture of a vehicle that we did for them that unfortunately ran over an explosive. But everybody inside was still alive after that. So it was really cool to see. Green opportunities. I know Barack Obama has been pushing for green opportunities, helping facilitate, fund those things like solar cells, glass, wind turbine blades, lightweight materials. There's a company out here that takes round-shaped glass. We actually take a 5-axis head, bring it inside the bowl, and then cut out a little square in the center. And that's where the light will actually hit the bowl, reflect into that, and bounce off and give solar power energy. So all sorts of different types of applications. So this right here, if you go to our booth, this is our new dynamic XD cutting head. What makes this interesting is in the past, you have your 5-axis cutting, but you also had to manually calculate and pull off the taper from it. So what this is doing is actually taking our dynamic Waterjet, the one that we saw, the little slight articulation. It's doing that at the same time it's also cutting angles, so you're cutting accurate angles. And again, so these can produce angles with 1/1000th of an inch of tolerance. So the part that was being passed around, the sear ring that I mentioned, that little circle round part, it kind of had angled cuts into it. That was a part that was actually part of this case study. So there's a company called EMS. They basically had a 5-axis plasma machine, wanted to expand their capabilities, speed up the cutting process, wanted a more accurate part, wanted to eliminate some of the secondary processes because, again, when you deal with plasma cutting, it's melting, so after that they had to sand it down, grind it down, and they just wanted to save overall time. So this is the part before. So this is multi-axis plasma cut part. Took about 120 man-hours to do. Really low tolerance, which was needed for them because they actually had to put the parts together and weld it all together. And they needed some elaborate fixturing just to hold that part together. So this is what was done with the Waterjets. So the part that was passed around was this front piece here. It was really fit nicely together. You actually didn't really need to tape it up or hold it together. It was that tightly nested. Took about 50% less time to get this part cranked out. Just overall a much more attractive part for the end user. So here's a side-by-side example. Again, you can kind of see the burning that the plasma left. Just not an attractive part. It just took a lot of time to get it even to this stage. And then again, this is actually only one pass with the Waterjet. We never go through and cut parts out over and over. It's always a one-pass deal. So you can kind of see a side-by-side sear ring. And the reason why it's called a sear ring is this part is actually used for Subway sandwiches. So what they do is they actually heat this part up till it gets like really red, it's like glowing, really hot. And then they take their real chicken breast and they lay it over top, and then that's what gives it the grill marks, the little hashed grill marks on top of it. So we'll wrap things up. We took a look at some of the different types of processes. Why Waterjet has a really strong future compared to things like your plasmas and lasers. It's just cheaper, faster, more accurate. Then now again, introducing the dynamic XD into the mix, getting accurate 3D cutting. So that's all I have. And I guess we'll have kind of a Q&A if anybody has any questions. And again, our booth is over at 3435. So if anybody wants any sample parts cut, you can actually see it. And then it takes about half an hour, 45 minutes. And then after we're done with all the cutting, we'll pop them out. You had a question? Okay, so I think I heard the question right. So based on like different surfaces, different material types, when you're cutting, is there any abrasive spray or splash? Is that any like deflect or anything like that? When you're, there isn't. What we actually have, we have splash shields that go up. Typically, you can also cut underwater if there's any spray. Actually, cutting underwater keeps the stream more coherent, so it keeps it together. But again, it also reduces sound, it reduces any type of splash. And as far as what you deal with, as far as like spray or anything like that, the only thing that you're really getting is the steam and the mist. And then what typically happens is when you first initially punch the material, it's going to create that mist. And then as soon as it goes through, you don't have to really worry about any type of spray or anything like that. Yeah, yeah. Are there any other questions? Nothing? Yeah. Water consumption? You mean like recycling or filtering? Yeah. Now, it really depends on the county, the location that your shop's at. They have different regulations. Before the water comes in, it goes all the way down to a 0.5 micron filtration. Goes in the system, goes out through a water vapor system, which is kind of a 3-step filtration, and then goes back through a 0.5 micron filter and then back out into the drain. Now, we even have people who use well water because well water is our only source. And the only other obstacle is when you deal with like your hazardous material, because as soon as you cut hazardous material, it infects all the water. So sometimes what we do is we'll fill up a barrel of water and then use that as the catcher tank. So we'll cut over that barrel. So the water is all contained within that barrel. We seal it up and then you can just take it straight to, hazardous locations at wherever they recycle it. Yeah. Are there any other questions? Well, again, we're at booth 3435. Any of us in white shirts, just feel free to, if you have questions or if you see the live demo going on, you guys have questions, just feel free. So, thank you.